Now we come towards the Fleming's right-hand rule. As we have discussed earlier also, Fleming's right-hand rule is indicating that if we stretch forefinger, the central finger and the thumb at right angles to each other, then magnetic field is indicated by forefinger and the motion of conductor, that will be by, or we can say that induced current will be indicated by central finger and the motion of conductor by thumb. So this law is used for finding the direction of induced EMF or current. According to this law, if we stretch the right hand thumb and two nearby fingers, these nearby fingers are central finger and the forefinger, perpendicular to one another, and first finger points in the direction of magnetic field, that is we are referring to forefinger direction, and then the thumb in the direction of motion of conductor, then the central finger will point in the direction of induced current. Direction of induced EMF and current. This is basically we are referring to application of Lenz's law. Whenever we use Lenz's law and Faraday's law, only negative sign is to be considered during the expression. And if we are purely using Lenz's law, we normally take the magnitude of certain numbers. If current flowing in the coil appears anti-clockwise, then that plane of coil will behave like a north pole as shown in the figure. And similarly, if the current flowing in the coil appears clockwise, then plane of the coil will behave like south pole. If the north pole of magnet is moved rapidly towards the coil, then according to Lenz's law, the induced current will flow in the coil in such a direction so as to oppose the motion of magnet. Wherever the motion of magnet is opposed, it means acceleration is slightly reduced. This will happen only when the face of the coil towards magnet behave as a north pole. That is, induced current will appear flowing in anti-clockwise direction as seen from side of the magnet. So, in the adjoining figure, we are finding here that the magnet is brought nearby, and there are two diagrams shown here. Galvanometer is indicated and there is a coil. Whenever magnet is brought near the coil, we will find same polarity will be induced. Thus, a force of repulsion will be produced between the magnet and the coil, because whenever a magnet is brought near the coil, first of all, same polarity will be produced, and as a result, repulsion will take place, and the velocity of the magnet will slightly reduce. The coil coming near each other, which will oppose the motion of magnet. Hence, some mechanical work has to be done to move the magnet near the coil against this opposing force. And this work, that is mechanical energy, is converted into current, that is electrical energy. Again, it is shown in the figure. The north polarity is produced on the coil, and that is causing the repulsion, and the flow of current is anti-clockwise. On bringing a south pole towards a coil, the current induced in the coil will appear flowing in clockwise direction, as observed from the side of magnet, and the face of the coil towards the magnet will behave as a south pole. On moving the north pole of magnet away from the coil, the current induced in the coil will appear flowing in the clockwise direction, as seen from the side of magnet, and the face of the coil towards the magnet will behave as south pole. Now we are finding in the figure that north pole is brought nearby the coil and opposite polarity is induced, and that opposite polarity will attract the north pole and velocity of the magnet will slightly increase. So on moving the north pole of a magnet away from the coil, the current induced in the coil will appear flowing in the clockwise direction, as seen from the side of the magnet, and the face of coil towards the magnet will behave as south pole. On moving the south pole of the magnet away from the coil, the current induced in the coil will appear flowing in the anti-clockwise direction, as seen from the side of magnet and the face of the coil towards the magnet, will behave like a north pole. So it is the inverse operation as we have seen in the earlier case. Now we have brought the south pole near the coil and opposite polarity is induced. If magnet is allowed to drop freely through a copper coil, then an induced current will be produced in the coil, and this current will oppose the motion of the magnet. As a result, the acceleration of the falling magnet due to gravity will be less than g. If coil is cut somewhere, then the EMF will be induced in the coil only, but current will not be induced in the absence of induced current. And we find the coil will not oppose the motion of magnet, and the magnet will fall through the coil with the acceleration equal to g. So again and again we are repeating our experiment and we are coming to the important conclusions. If a magnet is dropped freely in a hollow, long metal cylinder, then acceleration of falling magnet will be less than the gravitational acceleration. As the magnet keeps on falling inside a tube, its acceleration will continue to decrease, and after traversing a certain distance, the acceleration will become zero. That is, velocity will become constant. Now the magnet will fall with constant velocity. This constant velocity is called the terminal velocity. So terminal velocity is valid only when the magnet is continuously falling into the coil. So for some time we will find acceleration is there, but after a certain distance the acceleration will become zero, and we will say that the velocity of the magnet has become constant, and this constant velocity is called the terminal velocity. If current carrying coil is brought near another stationary coil, then the direction of induced current in the second coil will be in the direction of current in the moving coil. So in the figure it is shown that in the right side figure there is a galvanometer and a coil and it is stationary. But in the left side coil there is positive and negative of the battery. It is sending the current in the coil and the current will be induced in the stationary coil. If a current carrying coil is taken away from the stationary coil, then direction of induced current in the second coil will be opposite to the direction of current in the moving coil. Now see the figure. We are finding here that G is stationary, and now in this case coil is taken away from the stationary coil, then the direction of induced current in the second coil will be opposite to the direction of current in the moving coil. In the coils arranged in the following way, when the key K connected in the circuit of primary coil and it is pressed, an induced current is produced in the secondary coil. So that current is called secondary current. The direction of induced current in the secondary coil is opposite to the direction of current in the primary coil, and that is in accordance with the Lenz's law, which states that EMF is induced due to change in flux, and the direction of induced EMF is such that it opposes the cause which produces it. So what produces induced EMF? It is produced due to the change in flux. So direction of E and the change in flux will always be opposite. When the key is opened, then current in the primary coil is reduced to zero, but current is induced in the secondary coil. The direction of this induced current is the same as the direction of current in the primary coil, because current is decaying in accordance with the Lenz's law. So this is again shown in the figure, and when current is passed through a coil, the current flowing through the coil changes. Whenever we press the coil, the current will flow, and whenever we will stop pressing, the circuit will become open. As a result, the magnetic flux linked with the coil changes. Due to this, current is induced in the coil, and if current induced in the coil flows in the opposite direction of applied current, if the current flowing in the coil is decreased, then current induced in the coil flows in the direction of applied current so as to oppose the applied current. So again, it is shown in the figure. In the left side figure, the key is closed, and in the right side figure, the key is open. So when key is open, on decreasing the value of current, and here in the left side figure on increasing the value of current. So whenever circuit is closed, value of current is increasing. Whenever circuit is open, there will be no current. It is decaying slowly. Two coils A and B are arranged as shown in the figure. On pressing the key, current flows through coil A in the clockwise direction, and the current induced in coil B will flow in the anti-clockwise direction. This is in accordance with the Lenz's law. In opening the key, the current flowing through coil A will go on decreasing. This current induced in the coil B will flow in the clockwise direction. So again, it is shown in the figure. K stands for key. There is positive and negative of the battery, and A and B. These are the coils. Coil A and goes on decreasing. Current induced in coil B will flow in the clockwise direction. If current flows in a straight conductor from A to B as shown in the figure, then the direction of current induced in the loop placed near it will be clockwise, and that is also in accordance with the Lenz's law. So there is a straight conductor AB, we are passing current in it from left to right, and the current is induced in the coil and it is moving in clockwise direction. Now next is about three identical circular coils. So see the figure, the description is indicated. There are three coils. Now we are finding in coil A the current is anti-clockwise, and coil C. In coil A the current is clockwise, whereas in current C the current is anti-clockwise. Now what we find, three identical circular coils A, B and C are arranged coaxially. Coaxially means that their axes are same. The coils A and C carry equal currents as shown. Coils B and C are fixed in position. If coil A is moved towards B, then the current induced in coil B will be in clockwise direction, because the direction of current induced in coil B will be to oppose the motion of coil A. The face of A towards B is a south pole, then the face of B towards A is a south pole. There is no relative motion between B and C, so current will not be induced in coil B due to coil C.